Within Chapter 8, we spent some time looking at the energetics involving ionic bonding. In this video, we're going to look at the energetics of covalent bonds. Recall what leads to the formation of a covalent bond. So we saw that we could begin to understand this when we looked at the bonding of hydrogen atoms to result in a single bond in an H2 molecule. This was a covalent bond, a sharing of the electrons. The attractions that took place that led to this bond were based on the fact that the electrons could now be found when they were shared in the region between the two nuclei. A given electron could be attracted to protons in each atom. When we looked at representations of these two dots, or whether it was a single line, the key thing is that we had opposite charges attracting each other, attractions between electrons and protons. So when we're looking at these different representations, single bonds was referring to a given amount of electron density where the electrons were found between the two atoms. When we looked at aspects of single bonds having a bond order of 1, double bonds a bond order of 2, triple bonds a bond order of 3, what we're describing is differences in the electron density between the two nuclei. When I say electron density, I'm saying how many electrons are being shared between the two atoms. That's what we saw was leading to a particular bond. So if we have 2 electrons being shared, 4 electrons being shared, 6 electrons being shared, we're changing the density of the electrons between the nuclei. So let's consider how will this affect the bond. We'll look at things such as the length, the strength, and the energy. Back in Chapter 5, we introduced the topic of bond enthalpy. We saw that bonded atoms move to a lower potential energy than if the atoms were separate. Energy wasn't being stored in these bonds. This was the atoms moving to a lower potential energy. A misconception is that its energy is somehow stored in these bonds, and that by simply breaking the bonds, you get that energy released somehow. And that's not right. Energy is always produced when you're forming the bond, and it always takes energy to break the bond. The amount of energy involved in typical bonds, in Chapter 5, we described that as the bond enthalpy. If we consider the bond enthalpy value as the energy it takes to break a typical bond, we viewed it as a positive value. What if the bond's formed? Then it was being viewed exothermically. So we could look at the same magnitude and consider, is this the amount of energy that it takes to break a bond, or the amount of energy released when a bond is formed? A lower potential energy I view as a stronger bond, and it has a higher bond enthalpy. Let's connect this to the idea of electron density. If we compare single bonds between carbon atoms with double bonds, or single bonds between oxygen atoms with double bonds, we see that as we have a higher bond order, there's greater electron density between the nuclei, and that's leading to a higher bond enthalpy. I go back to all of these terms now, and I can add to it the idea of bond order. As the bond order is going up, the potential energy is going down. It's becoming a stronger bond, and it has a higher bond enthalpy. We did calculations involving bond enthalpy for a reaction like this. I think we now have added the skill where we could draw these molecules. And in fact, we could do even better. We could add the lone pairs that the authors omitted. When we had the provided data, we calculated whether the reaction was exothermic or endothermic by looking at the energy that it took to break the bonds, and then the exothermic contribution during the forming. We can now understand this better. Why is this reaction exothermic? The bonds in the products are, overall, stronger at a lower potential energy than those in the reactants. If we look closely, something like CO2, a carbon-oxygen double bond, that has a very high bond enthalpy. I'm forming a lot of those in the products. This is explaining why the overall reaction is exothermic. This is true for all combustion reactions. Combustion reactions are always exothermic because overall the products that I am forming have stronger bonds than those in the reactant. In section 8.8, we're going to look at the strengths and lengths of these covalent bonds. We're going to correlate the bond order with their strength and their length. We're going to see how those fit together. So here we have some data for nitrogen, whether I'm looking at the single bond, the double bond, or the triple bond. Is there a relationship between the bond length and the bond enthalpy? Sure looks to be. When I have the bond getting longer, I have the bond enthalpy decreasing. This is a weaker bond. It is a longer bond. It looks like my N triple bond there is a shorter bond, and it's a stronger bond with a higher bond enthalpy. Take a second, see if you can make predictions. If we're talking about bonds between carbon atoms, if they're single, double, or triple, how do you think the bond length compares? Or between carbon and nitrogen, or between carbon and oxygen? For each of those three sets, make a prediction in terms of the bond length. Which bond is shortest? Which bond is longest? Now let's add to that. Also make a prediction for the bond enthalpy. If we're looking at carbon-carbon bonds, if they're double bonds or triple, carbon-nitrogen, carbon-oxygen, make a prediction for each set there. Tell me about the bond enthalpy. For the bond length, we see that a single bond is longer, and it's getting shorter as the bond order increases. This is true for carbon with carbon, carbon with nitrogen, carbon with oxygen. Connecting that then to the bond enthalpy, a triple bond is a stronger bond. It has a higher bond enthalpy than a double. And that's true in each case. So as I'm fitting together these ideas, the way I conceive it, a strong bond is a shorter bond. There's a stronger attraction. It has a higher bond enthalpy. It has a greater bond dissociation energy. This is the energy that it takes to break the bond. It would result in a lower, more negative potential energy value and a higher bond order. All of these are terms that I'm fitting together when I'm thinking about a strong bond. How do these then relate for a potential energy well diagram? Let's explore that. So here we have an atom that's outside of the potential energy well. It's at a larger distance. It's further away. As the atoms move closer together, distance is getting shorter, potential energy is going down. I think this is a potential energy well that could describe a single bond. Bond order of 1. If I were to say, what does a double bond look like? Bond order of 2, it would be a lower potential energy, and it would be shorter. This would be a double bond. What would a triple bond look like? Well, I know it would be lower in potential energy. Is it longer? No, it's shorter yet. So what we're connecting here is this potential energy well diagram with all of our descriptions then for what characterizes a bond. What might you be asked to do with this information? So here are some end of chapter questions. 8.71, these might be in the conceptual category or the conceptual classification. These are about the ideas that were shared in this video. 8.76, it's now being connected to Lewis structures. You're asked to draw Lewis structures for two different things, an ion and a neutral molecule, and now do comparisons involving aspects of the bond length. And then finally, we now have the skills so that we can use provided bond enthalpy data, and it might be a case where we have to draw the molecules first. We have to draw the molecules and determine if they are single, double, triple bonds, and then look at the table accordingly.